Hello, students. Very good morning to all of you, and I welcome you back to my class, Physics 2. It is going to be our 32nd lecture. It's a long journey you have made, and now we are talking about very seriously about electromagnetic theory. I told you we are learning electromagnetic theory in few steps. Primarily, we have to know about vectors, the vector calculus, differentiation, and integration, divergence, curl, etc. And integration is some of the theorem like line integral, surface integral, and volume integral, because all these mathematical operation in terms of vectors have got huge importance. Everything we interpret in electrostatics or magnetostatics or electromagnetic theory is in the language of the vectors. So basically that's why I put few discussions on vectors initially. After that I moved into this electrostatics where charges were static. Now when charges start moving, we've got steady current, and that has resulted into magnetostatics. There is a study of creation of magnetic field due to the flow of charges in a definite rate, so the current is steady. Flow of, because of the steady current, the Bar-Savart law was our last topic. So today objective of the class is that we'll be talking about the another law in the study of magnetostatics, which is popularly known as Ampere's circuital law. Ampere's circuital law is going to tell you, is going to describe you the again the production of magnetic field due to a current loop. Okay, whatever be the amount of magnetic field created by the current loop, and what is the amount of current content inside the loop. So all those things are integrated actually through the Ampere circuital law. So that is the main objective of the class. We will talk about the Ampere circuital law. We will solve some problems on Ampere circuital law. So the main outcome of the class will be that after ending the class, you will be able to explain the concept of few things. Why magnetic monopole don't exist. That you will get from the Bar-Savart law. Whether magnetic field is rotational or irrotational, whether there is any vorticity of the magnetic field or not. How do you find out magnetic field at a given point in a particular problem using the idea of Ampere circuital law? So all these things we'll be able to do after this class. So students, let us move into the actual discussion. But before getting into that, as usual, I'll spend few minutes to just remind you the basics of vectors, because that is everything in this class of electrostatics and magnetostatics. Okay. Now these are common. This is me, which if you know me. Okay. Now here in these are the concepts of basic vectors. The concept of gradient, divergence, and curl. You know, with a gradient of a scalar, divergence means flow of a vector that will be inward or that will be outward, and curl is the vorticity of a vector. Okay. This is divergence, temperature as the divergence. Okay. There is a change. Temperature as the this is the gradient. Sorry, very sorry. Gradient will take a scalar function, that is the temperature, and you see it is irrespective of the direction. Okay, it varies. If there is a, well, I had this lot of discussion I made. Okay, in this journey, some with some beautiful animated pictures that we can see on the screen, and these are the basic gradient operator. Now the divergence, that means flow. You can see flow may be outward, is positive, flow may be inward, divergence will be negative. There is no flow. Okay, there is zero divergence, as you can see in the uniform field. So these ideas will be needed today. Okay, this flow, the divergence. We'll talk about divergence of a magnetic field. Okay, so these are the concepts. Okay, this is related to the electric field. You see, there is a flow of the line of forces, like in this case, electric line of forces. Now this is a very popular operator, Laplacian operator del square. And now the concept of curl. Curl means rotation of a vector. Okay, this is a rotation means curl, or you can see the ampan there. Okay, the rotation of the velocity vector. Okay, now line integral means about basically work done over a circular path. Surface integral means total flux coming out of a surface. Okay, there is, you can see, f dot ds in nds is basically unit normal to the surface ds. Okay, and volume integral means you consider a minor small volume, you have to integrate it over the entire volume. The relationship between divergence theorem, the volume integral and the surface integral is given by Gauss's divergence theorem. Relationship between the line integral and the surface integral is given by the Stokes theorem. Okay, as you can see, this is a Stokes theorem. Stokes theorem in today is called Green's theorem. All these things I discussed. So now I'm not talking about electrostatics. You see, just to remind you, the electrostatic field, you see, there is a net flow from a positive charge or negative charge, whatever you see. So the divergence of electric field is always non-zero. I'm repeating it time and again because in magnetism today I'll talk about divergence of magnetic field. So there we'll see how the change is taking place. Okay. These are the basic definition of electric field, force on a unit charge. Okay, the concept of Gauss's law of electrostatics, total electric field coming out. Okay, the Gauss's divergence theorem also you can see on the screen. Okay, Gauss's divergence theorem you can see on the screen there. And now you notice, okay, flux density just changes in terms that because epsilon 0 E is flux density D. So these are the changes, but we are actually focusing on the magnetostatic part, which talks about the flow of the creation of magnetic field at any point P due to any current element ds. So position of P with respect to ds will be theta, and current element will be I ds according to my drawing. You can see there the formula is that this magnetic field produced at the point P due to the current element IDS is proportional to the current element, that is IDS, is proportional to the angle between the direction of the tangent to the curve, actually the length element, the current element, and the point P. Okay, the related position vector may be r cap, the unit vector in that direction. And so basically that angle between IDS and R, as you can see there on the screen, which are indicated by a symbol theta. So basically it is proportional to the sine of that angle and inversely proportional to the length square r1 by r square. So to remove the sign of proportionality, we have brought in a constant mu0 by 4 pi. So the expression of the magnetic field at any point P is given by mu0 by 4 pi IDS cross, okay, because IDS sine theta is the cross product, okay, IDS cross r cap by r square. So what I did the other day, we applied this idea of Biot-Savart law in the solution of some physical problem where we estimated magnetic field in specific cases. Now, these are all the cases. There is a magnetic field due to a wire. That force is basically dl cross b type force. Okay, it is shown there. So the force was calculated as force per unit length as mu0 I1 I2 by 2 pi d, the separation. Okay. Now magnetic field due to a long wire. This calculation I have done last day. What you can see on the screen, it is Biot-Savart law followed by an integration of dV over the entire region over length. So it becomes B. So only sine theta ds r square. Okay, as you can see on the screen. Okay, as you can see on the screen that the sine theta ds r square. And r square from the geometry of the problem is a square r square. Sine theta is sine pi minus theta or pi by 2 plus theta, whatever you say, you like, no problem. So if you do it, that is r by r square plus r square. So if you put all those values and now do the calculation, it is mu 0 I by 2 pi r. Okay, under the limit of a long wire. Okay, 0 to infinity is the length. Okay, if it is an infinite wire. So this problem I did yesterday. Magnetic field due to at a given point P due to an infinitely long wire. Okay. So now if we move forward, you can see the same problem is coming in a different way for a circular current loop that you also calculated mu 0 I by 2r force between two charge to play to conductor. Okay, that you can also see on the screen. Now this is a very funny picture. Okay, you see that is a two conductors are there, the force between two charges that is shown there. Okay, this formula. Okay, the force is given by mu 0 L, the length element. Okay, and the current I A I V by 2 pi d. I and I V are the two currents passing through the wire. I did it, and D is a separation. Okay, so if you look at the description, the force is inversely proportional to the separation between the plates, between the conductors. Okay, and directly proportional to the current passing through. Obviously, length of the wire. All these things are deciding factors. But if they are far apart, actually, the effect of the magnetic field or magnetic force on the body because of this effect is actually it has to be not so prominent. Okay, D, it will fall with D. Okay, if we increase D, so you can see there's some wonderful animations how it changes. Okay, you see those yellow one, you can see. I just mark it. Okay, these are the two loops. Both of them are carrying the current, and you can see here also two current carrying loops. These are the two loops, and you can see there. Okay, two conductor, the force between them, that same issue. Now here I got a very funny and interesting topic for all of you, popularly known as the Ampere's circuital law. You please see what is written here. Okay. You see, I've taken a closed circular loop C. C is a closed circular loop, and you can see here it is enclosing various current elements I1, I2, I3, I4. And outside this encircled region, outside this zone, I should say, there are two current elements, I5 and I6. And current element may be source of current or current element may be sink of current. So I've got a curve C or enclosed C is there which is enclosing few current elements. Now the idea is that the Ampere circuital law states that is the net current, if you look at the problem, is basically the summation of all the currents. Okay, the I1, I2, I1 and I2, I1 is in the upward sense, sorry, downward sense. In my drawing, I2 is doing the opposite. I3, okay, let it be in the same sense, and I4 is doing the opposite. So that is the net current. Okay, through the to this conductor, I should say. Okay, and we have chosen a small length DL. Chosen a small length DL here on the wire. There you can see that. Now I wish to calculate, that is, line integral of the magnetic field over the closed loop. So net current is I is me, okay, I1, I2 minus I2 plus I3 minus I4, minus signs are coming. whether that is source or sink of the current. Now, the Ampere circuit law tells us there is a line integral of the magnetic field over the closed loop equal to mu 0 times the amount of current contained inside the loop. So it will be line integral B dot dl, okay, and mu 0 I stands for all those individual current summation. I1, I2 minus I2 plus I3 plus I4 is the net current. So bias about Ampere circuit law states that actually line integral of B dot dl, the integration of the magnetic field over the closed loop line integral B dot dl is equal to mu 0 I, the net current. This is Ampere's famous Ampere circuit law. Line integral of B dot dl, magnetic field line integral, equal to mu 0 times the net current enclosed inside the loop. Okay, this is some that concept. Okay, now very similar ideas are given. The line integral of B dot dl is your working formula here, which is coming from magnetostatics, and similar formula we got in electrostatics also. I talk about electric fields, that is surface integral E dot ds is equal to q by epsilon 0. Okay, so these are the two basic and working equation. If you compare the world of electrostatics and the world of magnetostatics. Now, I request you to look at this equation very carefully. Line integral B dot dl mu 0 I, you can see there, this is the expression of the Ampere circuit law. Now the current element I is surface integral of the current density J. I hope all of you can see this. Okay, surface integral of the current density J. Okay, this one. So basically in this expression I can replace this I with the help of this equation, and that is what we did. Surface integral J dot ds is the okay. So now surface integral J dot ds, this term that you can see on the screen, surface integral is connected with curls with the Stokes theorem like this way. There is line integral of B dot dl, okay, is equal to mu 0 times surface integral of J dot ds that you can see here. Okay, now by Stokes law, we can actually write down B dot dl, which that is a line integral, is equal to curl of B, okay, surface integral of ds. Okay, so we can replace that B dot dl is equal to curl of B dot ds. So it becomes mu 0 surface integral of J dot ds. So basically, this term here has been replaced with the help of this equation. Okay. Using Stokes law, we have done the replacement. So now it is like our surface integral of B, curl of B dot ds is equal to mu 0 j surface integral of ds. So here this is also surface integral. Left hand side also for a surface integral. By comparison, we can write down curl of B. Curl of B is equal to mu 0 j. This is the Ampere circuit law that you can see on the screen is in differential form. Okay, Ampere circuit law is in differential form that you can see on the screen. So this is a summary of the discussion. Okay, you can see differential form of Biot-Savart law is divergence of B is equal to 0, and on the contrary, Gauss's law is divergence of rho is equal to rho by epsilon 0. So the conclusion of Gauss's law was that there is a net flow, it is non-zero. There is a net flow of electric field lines. Okay. On the contrary, in the divergence of B equal to 0 is very important. It's actually one of the Maxwell's laws. It tells us there is no net flow of magnetic field. So that means if you have got a bar magnet, the magnetic north pole is there. Whatever be the magnetic lines of force coming out, whatever be the magnetic field, okay, whatever be the magnetic line of force is coming out from the north pole, suppose it is north pole, it is the south pole. Whatever be the line of force, it is my line of force it is producing from the north pole, this will be entirely going to the south pole or vice versa. That is, if it takes any magnetic line of force, whatever is coming out from the north pole, so there is initial flow, but this is acting like a sink in the source. Okay, so there is no net outward flow of the magnetic line of forces. So this tells us if there is no net flow, whatever be the line of forces that is emitted by the north pole, that must be collected by south pole. So for magnet, therefore you need exactly two only you need two poles. Okay, otherwise this situation cannot be satisfied because suppose I've got a single pole, then what would happen? Suppose only north pole I have. Okay, so magnetic line of force will come out. Okay, magnetic lines of forces will come out. Okay, but if there is no south pole, who will act as a sink? Because this is the source of magnetic line of forces. We need a sink to do the job because there is no net flow. If this is true, then I have to put a this is not I have to put right now divergence of B is non-zero. But I know divergence of B is zero. So that means if there is a net flow, there is a flux lines coming out of the north pole, there must be an opposite pole to accept it. Okay. So ultimately there will be no net outward flow of the magnetic line of forces. So it's a very immensely important idea. There is no net outward flow of the magnetic lines of forces, but for the electric field part that we discussed even before also, there is a flow. Now the curl of the differential curl of magnetic field is non-zero. Few minutes back I have shown you also. So on the contrary, curl of the electric field is zero. So magnetic field is irrotation. Magnetic field is curl is non-zero. If it is zero, okay, there is no net vorticity of the electric field or magnetic field you have. Okay. So this is all about this basic summary of the discussion related to the magnetism so far, and I compared side by side with our earlier discussions on electric field. Divergence of magnetic field is zero, divergence of electric field is non-zero. Curl of the magnetic field is mu zero times the current density of the current closed by the loop, and that is nothing but okay. On the contrary, so curl of B mu 0 G means so there exists if there is any current element there will be magnetic field. Okay? And another important idea is that if the curl of E is zero, so for electric field there is no net outward flow. So now let us very quickly solve few problems so that okay we can do some applications of this Ampere's idea.
I will start applying the Ampere circuital law. Before that, get into the expression of the electrical, the connection between the electric field and the potential energy, and that would going to help us in getting many expressions. Okay, so let's give some time to settle down. So look at this expression of the, I've got a current element IDL and any axial point P I wish to calculate the magnetic field. Okay, and this dB, the expression of dB is given by this much. IDL sine phi. Phi is the angle that is defining the point P with respect to the current element IDL, and it is very popular, IDL sine phi by R square. Now the question is that if ideal sine phi can be written as the dl sine phi is basically dl cross product with arc of vector. Now current density term therefore is given as I by A, you can see that. So now we can now write down the classical expression of the current density, which is also I by A. A means basically dV dl. Okay, basically the, you can see there, it is basically volume element by the length element. So then there you get the A. So J dV is equal to IDL. So now if I replace that IDL term with J dV, so automatically the equation gets into its form. Okay. So now let us get into this differential form of Bal-Savart law, divergence of B mu 0 by 4 pi. Okay, this J, the current density expression that we have achieved, we replace it now. Okay, and R square is already there, that has been obtained. Okay, so basically you can see this quantity J R prime, which is a function of the source coordinate, and we can also see here on the screen that is the, you can see there, it is very clear now. If I, and it is becoming like divergence of curl of two quantities J, which is a replacement of the current expression R by R square. Now I can use another idea, because we already explored all type of vectors identity. So divergence of curl of any vector is given by this much: B curl of A minus A curl of B. Okay, curl of A is basically, okay, now curl, you see the curl of B is there. So if we replace it, okay, so divergence of J, it will be equal to mu 0 by 4, mu 0 by 4 pi is there already. Okay, divergence of J is like A, so it is basically curl of J minus JR, curl of R by RQ. And now obviously you can see the next term will be like this much. This gives me divergence of B equal to 0. Okay, curl of J, that expression that I was talking about, mu 0 by 4 pi curl of J, JR, R prime is the expression. R prime means that it is a function of the source. Supposed to be the source function, and okay, and that curl of R by R curve is also 0. So the expression is not taking a shape like this one, and you can see it on the screen. Now let us apply Ampere's law in some specific problem. If you look at the, we have considered a cylindrical surface, and obviously B dot dl is equal to mu 0 I, okay, which is basically I1, the current walking to the device. Okay. So you can now actually, I by R square, you can write down the expression of the current. R is the capital, R is the larger radius of the wire itself, and smaller is basically the defined current element, it is radius. It is basically, it is fluctuating, you can see here. So the expression is I by pi R square. So you see, obviously you can change it. So B dot dl mu 0 is okay. So if I replace the expression of I1 with I r square by r square, and B dot dl, the denominator is r, so this is B dot B 2 pi r. Okay, so this is mu 0 I r by 2 pi r square. Okay, that is the expression. It is basically, if you plot it, B versus I, if you make the plot, the linear equation is going to be, and so dependence is basically linear. So now, if you look at this expression here, this is I, the current term, there is a current to the device, okay. So in this case also, r prime may be another point, so 2 pi r prime is the diameter, is the peripheral length, and I1 is there. Now this is the final plot, okay. It looks like this much. Now that you can see, capital R is for a point outside the region, small r is there, and so okay, you can see the plot here. Okay, everything will be clear to you. With this thing in mind, let us explore the action of the tunneling jar. And you can define a small current element that PQ is. PQ is inside the lane in the directional current. PQ length is within. So if I calculate the total current of V dot dl, the V 0 I, so that current is contributed by all, but here in this picture something will happen along the wire, which is still inside the wire. Uh, okay, this is actually two components will cancel each other, two perpendicular components, and components are coming from two horizontal components. Okay, so with this in mind, okay, so one is along the direction of motion, another is perpendicular to the motion of the electrons. So accordingly, you can see it on the screen, that is how it is varying. Okay, so for the rectangular PQR is B dot dl means P2Q, that is non-zero, and P is being processed, and you can see that. So obviously B dot dl, I have mentioned, okay, and inside the wire only it will contribute for the length element, and if the number of turns, if it is defined like this, length L, the total number of turns will be NL. Each turn carries I, the current passing through the area, and to the PQRS element would be, okay, this much, mu 0 Ni, as you can see it. Okay, these terms don't contribute. Now circular solenoid is called a to right, it is a circular shape is there. Okay, so if I choose any point outside the conductor, inlay solenoid in the form of a character circular path. You can see it on the screen. And outside the point it will be 0 as I mentioned, because it is not enclosing in current loop. Okay. Now another wonderful and funny idea. This is equal to minus grad phi of d by d of us now. From electrostatic divergence of is equal to rho by epsilon 0. So therefore we ourselves have got okay, another expression is coming. Del square v rho by epsilon 0, that is a Laplace equation because minor statics. Okay, so you can write down this in this way. Now if I get back to the PowerPoint presentation again, these are some of the basic, basic things every day I mentioned. Okay, so with this we conclude. Now next we talk about the magnetic vector potential.